Okay, great, thank you. So I have been kind enough to be loaned Hector's watch, so I think we can keep to time here. And I basically changed the title slightly because I wanted to be a bit more inclusive than just multipole expansion. So I'm going to talk about triangulating the universe's laws and contents with the three-point correlation function. So I'm a postdoc at Lawrence Berkeley National Lab, by the way. And first of all, I'd like to say thank you to the organizers for choosing a nice place to have this conference. I know some of you have been tempted to go to the beach instead of hear about three-point functions. I can't blame you, but we'll try to make it entertaining for all that. So here's an outline. I want to talk about why and how. Why, in terms of the data landscape, that's going to be upcoming, and that Will very nicely reviewed earlier this morning, and Hector also said a bit about. In particular, I also want to identify 4 physics areas that the three-point function can help with. So the three-point is a fairly technical subject. Talks on it can get boring quickly if you go into the details, although I will show a lot of equations later on, so stay awake for that. But I thought putting the physics forward would be nice, actually talking about what problems the three-point function can address. Then I want to talk about how. How do we measure it, model it, and match model the measurement? I thought, the 3 M's would be a nice way to remember that. And throughout, I want to take a synthetic approach where I talk both about the history and give you a sense for what people have been doing in the last, say, 20 years in the field, as well as to give you a bit of the cutting edge, actually say, what I think the new things to do are and what some of the new progress is in, different aspects of this, both why and how. So with that in mind, let's proceed. So here is some, certainly not an exhaustive list of the major questions in cosmology. One is, how do galaxies form? You might say we don't care about that in cosmology because, that small scale is baryons. It's for people who like to do detailed simulations. But I think we do have to care in cosmology because we select galaxies based on their baryonic content and what we see. But the cosmology is really in the matter distribution, which is mostly determined by the dark matter. So we actually need to understand the connection between galaxy formation and the underlying matter density field if we want to use galaxies for cosmology. Secondly, what is the full theory of gravity? We know that general relativity and quantum field theory at some level are like irreconcilable partners who have gone through a very nasty divorce. Fortunately, it's been long enough since the divorce that, us, the kind of kids, are not suffering too much from it. But we know as we go back, to the beginning of the Planck scale, that they just don't work together. We'd like to find out the theory of gravity that does work with quantum field theory. And, there are a lot of modified gravity aspects. Hector, fortunately, talked a lot about that, so I'll go light on the theory motive and, come back to this. And then 2 other questions are, what are the initial conditions? We think inflation ended with a Gaussian random field, but we'd like to learn more about the properties of inflation, and I'll argue that large-scale structure provides a great way to do that. And finally, a big one, last but certainly not least, what is the nature of dark energy? So these are some major questions that I want to show you the three-point can make major progress on. So now, what is the data landscape? Well, I'll quickly go through this because Will talked about this a lot. Current is, loss, EBOS, and DES, which is photometric. And in the future, we're going to have the dark energy spectroscopic instrument, which I think has the potential to be a game changer for cosmology. As Will said, it's like going from, well, actually, Will said that about Euclid. But I think even DESI is like going from doubly mapped to Planck in terms of what it'll do relative to BOSS. It's basically getting at sub% precision on the BAO scale, whereas BOSS achieves percent precision. And then in the sort of longer term, we have other spectroscopic missions like Euclid and WFIRST, and other photometric ones such as LSST. So here's just some eye candy. This is SDSS. It's a 2.4 meter telescope at Apache Point, New Mexico. At the bottom is the CMAS sample, which is color-coded by the redshift. So Eisenstein, I think, made this image. He's very proud of it because it shows you the closer galaxies are a different color than the further away ones. They're yellow, further away ones are red. This is just giving you a sense of what information we get when we do a spectroscopic survey. This is just the typical cosmic web picture, and this is giving you a sense of how this looks in time. Back here we have the CMB. Over here we have the cosmic dark ages. This is the map of the intergalactic gas, and then this is where galaxy surveys start to happen. So this is just more eye candy on the dark energy spectroscopic instrument. This is my view every day at Berkeley. Almost as nice as the Canary Islands, but a little foggier. And this is DESI Petal 1. As Will mentioned, mentioned, it has 500 fibers. Each fiber is going to sit on an 18-piece robotic fiber positioner, which this chair wants me not to be able to point at. And these can reconfigure the entire focal plane in 1 minute, so it's going to be a ridiculously high throughput spectrograph. So BOSS and eBOSS got about 1 million galaxies each, and DESI will get 30 million spectra, mostly ELGs and LRGs, and about 600,000 quasars. So this is just showing you BOSS and eBOSS to give you another way of seeing where we are. This is BOSS. It has 300,000 LRGs, 400,000 ELGs. No, I'm sorry, that's eBOSS. BOSS had about 800,000 LRGs in the CMAS sample, and I don't know the exact number for low Z. eBOSS has 300,000 LRGs and 400,000 ELGs at higher redshift. Quasars are going to be over here, and then the Lyman alpha forest gets even higher redshift. So that's data we more or less already have or will have in the next 6 years. So the question is, how will we use this data to answer some of the key questions of cosmology that I've outlined? And the answer to that is we're going to make a 3D map of the galaxy distribution. Maps are a traditional tool that enables discovery. Sometimes they enable colonization. Fortunately, we'll be stopped from that ladder because of causality. We can't get to the galaxies. But certainly, maps do help us when we're trying to understand what's around us. In particular, they let us search for patterns. Patterns, by their nature, repeat. And this, at left, is an example of something that's homogeneous, so it looks the same at any point that you sit at. If you sit over here, you're going to see the same set of lizards as you see if you sit over here. And this is isotropic, so if you sit at the center, it should look the same around you. And the laws of physics are supposed to be the same everywhere and in all directions. That's what we mean by laws. They wouldn't be that useful if they weren't. And so galaxy clustering, insofar as it's caused by those laws, should be also. I put a little red asterisk because we all know about RSD. We'll come back to that. But overall, we need a way to mod out translations and rotations, and correlation functions provide a means of doing that. So we'll very ably review correlation functions. This is just a slide about the typical estimator we use for the 2-point function. Basically, you look at the galaxies, you look at the randoms, you subtract them, and that gives you a measure of the clustering. Here I wrote it out as galaxy pairs minus random pairs over random, but in detail we do it in a slightly different order. But I just did this to make the example a little bit clearer for people who actually want to go through and calculate this and do the calculation. But it's basically what Will said. You have a line of a certain distance d, and you move it around your survey and ask how many things are separated by that line. And note here in this diagram, I meant things to be on a discrete grid where each of these little slices is d. But I won't belabor the point. Correlation functions are just measuring excess clustering above random. Now, for a Gaussian random field density, the 2-point function, or its Fourier space analog, the power spectrum, contains all the information. Intuitively, a Gaussian has a mean and a variance, it's a 2-parameter thing, so you would kind of expect that a 2-point function would get all the information. In particular, we know the cosmic mean density, that's like the mean of the Gaussian, although actually this is an overdensity field, so it has mean 0. And the 2-point function is a generalization of the variance. In particular, the 0-like 2-point function is actually the variance. But I'm here to talk about the 3-point function, which is excess triangles over random. I'm here to talk about that because the universe is not just a Gaussian random field. In particular, as Hector noted, you have nonlinear structure formation, and you have possible primordial non-Gaussianity. So those are both effects that give you a 3-point function of large-scale structure. Here's just a slide to show I did my homework. If you want to read it, go ahead, but it's basically summarizing almost all the 3-point function measurements I could find over the last 15 or so years. So you have a lot that have been done with SDSS. What I've done here is listed the types of triangles these probe and the number of galaxies. So this is 37,000 luminous red galaxies. They looked at triangles where the side lengths are ratio 2, 3, and 4 to 1. And the maximum scale they went to is 40 megaparsecs. Now with these measurements, it's always a little difficult to say what the maximum scale is because you really have 3 sides, not just one. So in this listing, I've just taken the maximum length of one triangle side that's achievable if you basically, open out the triangle, so it's longest. And basically, you can see in SDSS there's been a steady increase in the amount of data that's been used. We go from 37,000 in 2006 to some work that I did during my PhD with 800,000 LRGs from the TR12 CMAS sample. It's actually 770,202. And you can also see there's sort of been an upward trend in scale used, although most tend to concentrate on kind of smaller scales, this being an exception where they went to 90 megaparsecs, and then the work I did went up to 180. And then this is some work that was done with the WiggleZ survey, and this is a little bit earlier work that was done with 2D FPRS. So I just thought this slide was useful to kind of collate all the information. I'm not sure there's much deep to take away from it other than that. So here's just one slightly technical slide. Here's a triangle. Just to be clear, we were talking about triangles for the rest of this talk. There are different ways to parameterize a triangle. One is that you can use R1, R2, and theta, the enclosed angle between them. Another is that you can use R1, R2 over R1, and theta. And I've just mentioned examples of works that use these different parameterizations. And there's another parameterization that I'll show on the next slide that will be sort of a focus in the rest of this talk. I should also just mention the estimator we use for the 3-point function is called Zachary, and it's the analog of Lambda for 3 points. And basically, the idea is that if you screw up the number of randoms slightly, making a fractional error, this estimator nulls that out at first order, so it's only a second order error term, and that's the motive of the 2-point function as well. So this is just saying you take your data minus randoms, do the 3-point of that, and then do the 3-point of the randoms, and divide them. That gives you your edge-corrected 3-point function. So this third parameterization I wanted to mention is called the multipole basis. And the idea is to take the full 3-point function and write it as a series where you have these radial coefficients times Legendre polynomials for the angle enclosed. And so the nice thing with this is it really lets you visualize the 3-point function easily. You can basically say I'm going to plot these coefficients as a function of the two side lengths and at each multipole L. So this is just showing you the 3-point function dipole, L equals 1, and R1 and R2 here are the two triangle sides. And red is an excess of triangles over random, and blue is a deficit. And so this basis was actually proposed by Zachary in 2004, but no one really used it. My advisor, Eisenstein, and I during my PhD used it sort of with reasonable success for a number of algorithm papers and measurement papers. But it's nice because you can really see what's going on in the 3-point. So throughout the talk, I'll be showing you plots like this when I have to show you the 3-point. So I just want to note the 3-point function is potentially computationally expensive. It's basically this problem. If you have 10 friends and choose 2 to take to lunch, that's just 10 times 9, so 90. You can do that and still, take about 200 days off, 300 days off from taking lunch during the year. But if you choose 3 friends to go to lunch, you have 720 possibilities. You have to have lunch twice every day. So for large n, the 3-point function is basically scaling as n cubed versus the 2-point function is n squared. So this is a problem that I just want to get on the table at the beginning. I'll come back at the sort of mid to end point of the talk and tell you how to solve that problem. But now, what's the physics? Why use the 3-point function? I think it can address these 4 major questions. It can talk about galaxy formation by probing galaxy biasing. It can look at gravity via redshift space distortions. It can address initial conditions by looking for primordial ungaussianity, and it can do dark energy through BAO. So now I'll show you how. So what is biasing? Biasing is just you write down a lot of terms. In fact, the theorists are arguing you should write down every term you can by the symmetry that basically say that the galaxy over density that we observe is going to be some transformation of the matter over density. So the simplest bias model is linear bias. That's just saying it's a rescaling by this B1 number. Linear bias is like the contrast on a photocopier. It just says the galaxies trace the matter with some volume that's dialed up or dialed down. But then you have more complicated bias models that add a thing that's proportional to the square of the matter density. This Sij is meant to be a tidal tensor. T is for tidal, and BV is this relative velocity bias that Will mentioned, where you're saying that the galaxies somehow trace the relative velocity field between the baryons and the dark matter. And all of these are unknown coefficients, and you can think of this as a bit like a Taylor series. You're just saying you sort of have an organization by powers of the matter density plus other stuff, and you want the slopes with respect to each of this. So you can see the biases as derivatives with respect to different parameters. And I should mention that the matter field itself is extended in terms of the linear density plus the second order density plus the third order density. So this goes back to the perturbation theory talk we heard very nicely by Martin yesterday. And this is totally deterministic. You just say, I know my power spectrum and I know my physics, so you can calculate at least the statistical quantities of these. The biases, in contrast, are actually measured from a survey. So historically, Deckel and Reese, I believe, were the first to propose biasing in 1987. Nice perturbation theory review for this line is Bernardo 2002. And then there's a nice but massive, like 250-page biasing review by Vincent et al. From 2016, which you should try to read and then take a lunch break. But it's very nice if you want all the details about all the models that are possible. So, question with biasing, if we want to measure the bias, why can't we just use the 2-point function? Well, the 2-point function scales with sigma a squared times b1 squared, so it's actually degenerate. So you could fix sigma a from the CMB, but if you want both it and b1 for large-scale structure, you need to break this degeneracy. So the 3-point function, which I'm denoting zeta here, and I've written this clunky GGG to say it's 3 galaxies, scales with sigma a to the 4th times b1 cubed. So you can see if I square this guy and divide it by the 3-point function, I isolate a raw power of linear bias. And I break this degeneracy with sigma a. So that's super nice. That is an argument that actually goes back, I believe, to Fry 1994. So people already were thinking about this idea 30 years ago. However, redshift-based distortions also affect the measured bias. In particular, they enter so as to be degenerate with the linear bias. So we need a way to deal with that as well. So one thing people have done is they take the ratio of the observed 3-point function to dark matter simulations that have been redshift-based distorted using the velocities, which of course is a simulation, so you know the 3D velocity. So this is a plot from McBride paper about 2011 showing that basically the black is the matter, but with RSD imposed in this way, and the red and blue are actually SDSS DR6 measurements. And the point is that these curves, this is versus theta, the triangle opening angle, by the way, and he's chosen a particular set of side lengths. And so the point is these curves look like rescalings of each other, so you can just divide them and get the linear bias. The problem is that this approach builds in a simulation dependence into your reported results, because you're really saying I had to do my dark matter simulation and get this black curve to divide the data. So that's not ideal. And also, it's not a simple division if there are biases other than linear bias, which there are. So I do want to note, even on the theoretical level, remarkably, if you take the 2-point function and the 3-point function to leading order in the redshift-based distortion parameter, beta, where beta is f over b1 and f is the logarithmic derivative of the linear growth rate, then this argument about the ratios canceling the degeneracies out actually still holds. You can see when I square, sorry, this is missing a square. When I square the 2-point function, I actually get sigma a to the 4th, b1 to the 4th times 1 plus 4/3 beta. And that's the same way that beta enters the 3-point function. So the ratio argument from Fry 1994 still works. But we still have to assume only linear biasing, which is not really realistic. So let's be more realistic. We'd like to study bias terms beyond linear, so quadratic, tidal tensor, relative velocity. So this is where the 3-point function has a key advantage over the 2-point function, because these bias terms enter the 3-point function at leading order, which is 4th order in the linear density field, but these terms are subleading in the 2-point function. So in that sense, the 3-point function is a really ideal bias machine, because in the 2-point function, you're using one curve to look for many parameters, each of which is producing a small fractional change to the total signal. Whereas in the 3-point function, you're using many triangle configurations to look for these parameters, and each can produce actually an order unity change for the signal. So I'm not just going to say that, I'm going to show you a picture of that. So this is the 3-point function in real space, and sorry, sometimes one does go backwards. Right. Yeah, so this is the 3-point function in real space, and I split it out by the multipole moments. So this is monopole, dipole, quadrupole, hexadecapole. Actually, no, this is L equals 3. This is the hexadecapole. And also by bias coefficients. So this is linear bias, nonlinear bias, and relative velocity bias. And you can see that if you look at the linear bias, the relative velocity bias signal, for instance, is almost as strong intrinsically. Of course, linear bias is going to be of order 1 or 2. Relative velocity bias, the actual dB value will be much smaller. But the intrinsic signal that you're looking for to find these unknown coefficients is actually similar for the linear bias, which is the leading order 3-point function term, as well as these more exotic biases that you'd like to constrain. So just to show you in redshift space, the same thing, but now with tidal tensor bias. Here we have split out by multipole linear bias, the nonlinear bias, and the tidal tensor bias. You can see tidal tensor bias intrinsically is nearly as strong as linear bias in the three-point function in redshift space, although it has a little bit different dependence on the triangle side lengths. In particular, the linear bias has some different features over here that you can try to use to distinguish. And then this is just showing you the relative velocity in redshift space. Don't worry about the second column, but it's just showing you that, again, it's a similar magnitude and very distinct from the linear bias. So the three-point function is a great way to search for these biases. And some recent work I've done is actually to make very high precision constraints on relative velocity biasing using this technique, as well as looking at hints of tidal tensor bias with the velocity or 12 sample. So now I want to switch gears and talk about RSD. I said that I think the three-point can be used to probe RSD. This is just a picture. We've heard about fingers of God in a nice previous talk. These are due to infall, and on larger scales, not shown here, you have Kaiser pancakes, which are due to coherent motions. So for a nice review of redshift space distortions, everyone points at Hamilton 1998, so I will point at Hamilton 1998. But the point is, RSD are generated on large scales by coherent growth of structure, so therefore you can use them to probe gravity. In particular, it's this beta again. Beta is related to the linear growth rate, F, and F is in turn related to the omega matter, this 0.55 power. But this 0.55 power assumes GR and has a different value for other theories. So if you can actually measure beta and therefore get to F, you can measure this exponent and therefore measure what the GR is the right theory of gravity. So to get at RSD, what are our options? Well, one option is to use multiples of the two-point function or power spectrum, or wedges and angles to the line of sight. We'll review what both of these techniques are. And to get more information, you can try this ruling push to higher K. So a paper by Nick Hand et al. Shows that this is very, very hard. You have to use 19 free parameters, and that will roughly get you to K of 0.4 megaparsecs, but that only gets you a 15 to 30% improvement on F sigma relative to K of 0.2. So you're essentially doubling the range of scales you can use here, and only getting a 15% to 30% improvement, and getting a lot of free parameters involved in the process. So I would suggest we actually want to open up the use of the three-point function for RSD, because there are lots of triangles, and there are lots of ways for each side of the triangle to project onto the line of sight. So in principle, you should have many configurations that are all going to differently probe the RSD. However, in practice, the spherically average three-point function has beta degenerate with linear bias. So I would actually say we should try to use the anisotropic three-point function, basically track its dependence on angles in the line of sight, just like we do with the two-point function. So I'll come back to how to do this. I just wanted to set that up. Now, what to say about primordial non-Gaussianity? Just a quick one-slide summary of that. Generically, inflation predicts some deviation from Gaussian in field initial conditions. This is showing you the Bardeen's curvature perturbation, which is a gauge invariant curvature perturbation. And this piece is the Gaussian piece, and then you expect some square minus the expectation value of the square piece. Kind of analogous to nonlinear biasing or a Taylor series. Basically, just because the field is doing quantum mechanical fluctuations, you expect a little bit of this piece as well. And this F local is basically in Fourier space related to squeezed triangles, where one wavelength is very short and the other two are longer. There's also a equilibrial term, which has the most signal where all of the three Fourier modes of the triangle in Fourier space are similar. But anyway, the point is that these have theoretical motivations, for instance, higher derivative and DBI inflationary modulus. And a nice review of this is Sefusadi and Komatsu in 2007, and also Dan Bauman has some great notes on this. So, in particular, Caminelli and Zalbaraga found that the squeeze limit PMG in single field inflation is suppressed by this factor of 1 minus the scalar 1 minus ns, the scalar tilt. And this, because ns is close to 1, this is going to be close to 0 for scale invariant perturbations. So looking at the bispectrum or three-point is actually a very sensitive test of whether you have single field or multi-field inflation. So I think PMG is going to be a major goal of post-DESI large-scale structure. And that's because the CMB has led so far, but it's more or less saturated at FNL of order 5, modulo a slight factor of root 2 improvement when we add in the full information from CMB polarization. So we'd like to push down to FNL of order 1. That's what the theory says is interesting. But as I'll show, FNL of order 1 is very very hard with the 2-point function alone. So this is some projections that Pat McDonald at LDL did for a working group on what to do after DESI. And it's basically showing you the the standard deviation on FNL that you can get with these different strongman surveys. You can basically see that to get down to FNL of order 1, you need to use either 90 million ELGs and 10 million LRVs, or 10 million LRVs, but somehow get them visible out to redshift 4. So this is very challenging. I mean, DESI will get this number of LRVs, but they'll all be over here. Getting LRVs that you can actually see out to redshift 4 is probably not that realistic. I will note that this doesn't use some sample variance canceling techniques developed by Seljack and others, so maybe one can do a bit better than this, but I think it's pretty accurately pessimistic to do PNG with the 2-point function. However, the 3-point function is the leading on our statistics as compared to PNG. I will note a complication is that scale-dependent bias in the power spectrum can also reveal PNG, as shown by Neil Dalal. But that signature is on large scales, and again, you have one curve with many parameters and many possible large-scale systematics, such as survey boundary effects and dust, as well as cosmic variance is much larger on large scales because you have fewer of those large lengths inside a given survey box. So I think the 3-point function will still be vital for a robust detection of primordial non-Gaussianity. So now I want to just quickly move on to BAO. This is just a picture showing you what BAO do. I won't belabor it because we'll explain this, but it's basically CMB has BAO in it, large scale structure has BAO in it. We can compare these rulers and figure out how much is extended. This is just showing you the bump in the 2-point function due to BAO, and look at the error bars getting much higher as you go from DR9 in red to DR11 in black. So we're getting basically 1% measurements of the BAO scale with loss right now. BAO and the 3-point function also have a very distinctive signature. In particular, it's these red and blue creases at scales of 100 megaparsecs per H, which is the BAO scale in per H units. And you also get these diagonal folds, which are where the third triangle side that you don't see in this plot is equal to 100, and the other two are adding up to that. Basically, if R1 plus R2 equals 100, you get a diagonal line. So these BAO features can be used to study the BAO and the 3-point function. In particular, in my PhD, we made the first high significance BAO detection in the 3-point function. This is just showing you that our BAO lives in a chi-squared divot of basically 5 sigma relative to this no wiggle, no BAO model, which is in dashed red. And so the point is that once you have a detection of the BAO, the width of this curve shows you what this alpha is. Alpha equals 1 if we're in the right cosmology, but different from 1 if we didn't get the cosmology right. And the goal is to measure alpha, and the width of this divot is how precisely we can do that. So we can actually, using the 3-point function alone, measure the distance to redshift 0.57 with 1.7% precision. So that's not using any 2-point or power spectrum information, but just using these plots to measure alpha.
Sorry, do you need to worry about damping or anything?
This includes damping, so the models have a template. Yeah, we can maybe come back to that in the discussion, but you do use damping. So a complication here is that if you compare the unreconstructed 2-point function with the 3-point function, the 3-point function is like making loss 10% longer. So that seems like a win because for $0 extra and not much computer time, you get about 6 months of extra survey on a 5-year survey. But as Hector mentioned, and as Marcel Schmidtfeld and others showed in a theory paper, density field reconstruction brings that information nearly fully into the 2-point function. So that's not ideal because then you're not getting as much independent information. We confirm this empirically using mocks, just looking at 2- and 3-point function before and after density reconstruction. However, mocks do not have systematics, and data does. So it's actually still quite valuable, I think, to have an independent method of getting this information that doesn't rely on being able to do reconstruction. And in some cases, the sampling of the density is actually so sparse that you don't have enough information on the density to do reconstruction. So for instance, with quasars, it's just a very low number density sample, so you don't know enough about the potential to do reconstruction. So in these cases, the 3-point function is the only way to access additional BAO information. So we're doing an EBOS quasar BAO search underway right now. These are some of the folks involved in that. And this is at redshift 1.5, where there are really not many points in the Hubble diagram. So I think it'll be nice to have another way of getting BAO at that high redshift, and this will be a pathfinder for the much larger quasar sample in DESI. So we've discussed why do 3-point function. And now I just want to say a few words about how to do it. There are three major challenges of doing the three-point function. One is measurement. As I mentioned, it's n cubed, which if n is a billion is not your ideal scaling. If n is 15 million, such as it could be for DESI or Euclid, that's a really not ideal scaling. Two is modeling. It's a complicated thing. It has, as Hector said, multiple parameters. It's hard to visualize, it's hard to model. So how are we going to solve that? And three is matching measurement to model. In particular, the covariance matrix has been kind of the lurking hidden monster of three-point function studies. You always, in some three-point function paper from 10 years ago, find a paragraph saying, we don't really know how to do covariance, so we approximate it as X, and they just do something. So I'm going to outline some developments on all three of these points that I think make this realistic for next generation surveys. And just to note, previous three-point algorithms all basically used a KD tree to structure the data. This is just a spatial partitioning that you can use to more efficiently search data. And that sort of worked, but it's not ideal for galaxy surveys, which are very sparse, because for a KD tree, you want a lot of the points to be close to each other, so you can put them all in one leaf of the tree, and this is not really true for galaxy surveys on large scales. So I now want to show you this isotropic three-point function algorithm developed in my PhD that exploits properties of the multipole basis. This slide I've shown you before, so I just want to remind you, we want to find these coefficients. These are the radial coefficients that tell you how the three-point function depends on these Legendre polynomials in the opening angle. So how do we do this? Well, around each galaxy, denoted by the X here, we actually can expand the density field in spherical harmonics, and we can then use the spherical harmonic addition theorem to actually add those spherical harmonic moments up to get the Legendre moment around this point. So that's an order n process, and we still have to do it around every single galaxy in the survey. So overall, it's order n squared. But n squared is a lot better than n cubed. And in particular, this enables an algorithm that's 500 times faster than a naive triplet count for a 700,000 galaxy test case we did. And in fact, it's only 6 times slower than the two-point correlation function. So this algorithm has already been highly enabling for the three-point function cosmology. All the work that I referenced of my own going to very large scales and using the 800,000 LRT sample uses this algorithm. And also you get the anisotropic two-point function with the rotating line of sight for free, because the geometry is fundamentally the same. For the three-point function, you have a triangle, and for the anisotropic two-point, you also have a triangle, but these two sides are now lines of sight to the two galaxies in your pair, and here always the observer sitting on the vertex of the triangle. So it's actually a slightly simpler problem to get the rotating line of sight two-point function with this, and you can just report it at the same time. So I now also want to say, how do we probe redshift space distortions? Basically, recently I've been working on developing an anisotropic three-point function algorithm that first rotates so that the basis you use for your circle harmonics has the line of sight to the survey along the z-axis. And then instead of probing only the Legendre coefficients, you actually probe mixed coefficients that are just the product of the two spherical harmonics, but with different L's. So isotropy would force this L and L prime to be equal to each other, but when you have RSD, they break that. And the idea of rotating first so that your local expansion axis for the harmonics is the line of sight is that actually lets you a rotating line of sight for the three-point function. So this is just a nice picture showing what you do. You gather the galaxies and bin them in a sphere. You then rotate so that the global line of sight to the survey is the z-axis, and then you expand in spherical harmonics. And so we made a code to do this. We ran at scale on Cori, which is the 5th or 6th fastest supercomputer in the world at NERSC. So we got 5.6 sustained petaflops on 9,600 nodes, which is 80% of peak for the instruction mix we need to use. And you can obtain these harmonic coefficients you need with matrix algebra libraries. And so those are very fast because those are the things they use to do speed tests, in particular VGEM. So this let us do the three-point function for 2 billion halos in 20 minutes. And just summarizing, it will allow us to extract information on RSD from the three-point function. And in fact, we can do it for the entire observable universe of about 100 billion galaxies in roughly the time it took me to fly here using current computing resources. So of course, we won't have that sample for a while, but when we do, I will be ready. So I now just want to wrap up by saying a little bit about how we model the isotropic three-point function. I promised there would be equations. These are equations. So this is just a model for the multipole moments of the three-point function. So this is the monopole, this is the dipole, this is the quadrupole This is L equals 3. This is the hexadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadecadec of 1 and 2 dimensional integrals of the power spectrum, so that is very fast to compute. So these functions here, this C sub 1 and C sub 2 with a superscript 1 plus and 1 minus, they're just defined by these 1D circle Bessel transforms of the power spectrum. And in detail, we need these 2-dimensional integrals of the power spectrum too, because the redshift space 3-point function does some slightly more complicated things. But the point is that overall, this framework makes predicting the 3-point function very, very fast if you wanted to change the power spectrum. So I think eventually what one should do is actually say, we'll embed this in an MC-MC chain and just, add in different power spectra with different cosmology on the fly as needed and recompute the 3-point function predictions on the fly. So that hasn't yet been realized, but I think this formalism makes it fairly straightforward to do. So I'll just show you another piece of eye candy to compensate for the equations before. This is the full redshift space 3-point function with beta equals 0.37, which is the value for the CMAS sample. And gamma is the ratio of nonlinear bias to linear bias. And gamma prime is the ratio of tidal tensor bias to linear bias. So this is just throwing in some of the biasing that we think is actually there. And you can see you still get this very nice strong BAO signal at L equals 1, the dipole that you can use to do a distance measurement. You can also see that these higher multipoles don't look very different from each other, and that's because our basis is parsimonious. The 3-point function is a pretty smooth function of cosine theta, so you only need a couple powers of cosine theta to extend it. So you actually are not gaining much from these, and that's nice because then you can truncate and not calculate. Going to higher L, if you had to go to L of 3000 like in the CMP, that would be more challenging. So I just want to now show you 2 slides on how we match the measurement to the model. So this requires the covariance matrix. The covariance matrix is very high dimensional, and its inverse is actually dominated by the smallest eigenvalue, which is going to be the noisiest. So if you want to estimate your covariance from mock catalogs, you actually, as Will had a paper in 2014 showing, you need much more than 1 mock per dimension to render the matrix invertible. So for a 3-point function, that just demands basically a possible number of mock catalogs. So instead, what you can do is analytically compute the dominant Gaussian random field covariance and use mocks to fit for 2 free parameters, which are the shot noise and volume. And the nice thing with an analytic template is that it's going to be smoothly invertible. So just some equations showing you that this can also be done in terms of 1 and 2D integral transforms of the power spectrum. This is just a diagram showing the 6-fold symmetry of the covariance matrix and how you transform from Fourier space to real space. This is a test where we applied the inverse of our template to the true covariance matrix estimated from mocks, and then subtracted the identity matrix. If we did a good job modeling the true covariance, then this plot should look like basically noise, which it I think more or less does, and the fluctuations are quantitatively what you'd expect from noise. So just one note on cross covariance. You might want to combine fitted parameter values from the 2-point and 3-point function. And so you can use analytic autocovariance to fit these 2 functions separately, and then use mock catalogs to form the very low-dimensional cross covariance matrix of the 2- and 3-point function derived parameters, and then combine those parameters weighted by its inverse. So in other words, if you wanted linear bias from 2- and 3-point function, you would basically ignore covariance, fit for the linear bias from 2-point, fit for it from 3-point, then use mocks to get the covariance matrix of just the bias between 2 and 3-point, and then combine the biases weighted by the inverse of that. So we use this approach with BAO results from the boss 3-point function, and I think it works really nicely. And certainly you can do it with mocks because the matrix is low-dimensional. So in summary, the 3-point function is a uniquely powerful probe of galaxy biasing and primordial non-Gaussianity. And I'll remind you it's because the nonlinear biasing enters at leading order in the 3-point function versus subleading in the 2-point. And the 3-point function is also the leading order statistic sensitive to primordial non-Gaussianity. So I think it has discovery potential in both of those areas. And then the 3-point function also has the potential to add to standard 2-point function analyses on RSD and BAO. So